Good morning, ma'am.
Okay, so we can start off with the class, right?
Yes, ma'am.
Okay. Okay, so yesterday we discussed, we did revision on previous topics, that is compression and its techniques, right? So today we'll go on with image compression models. Okay, so previously we discussed what is image compression. That is some important concepts, and then that is we discussed the structure of image compression model, right? That is encoder and decoder. So today we'll go on with image compression models. Okay, so image compression models, we have two types. Okay, one is error free compression, that is also known as lossless, and one is lossy compression. Okay, then what is lossless compression? That is error free or lossless compression. Okay, so in lossless compression, what happens? As the name involves, there is no loss of information. That is, whenever you use this type of compression, there is not much. That is, you can't say no loss of information at all, but you can say that some part of information, that is very negligible amount of information, is lost. Okay, and that is not counted, or that is not uh, visible to the naked eye. Okay, so lossless compression, it involves no loss of information. Okay, then okay, so if data have been losslessly compressed, the original data can be recovered exactly from the compressed data. That is, in lossless compression, what happens? We have this interesting property. That is, if some information, that is, suppose you have got original data in hand. So suppose you want to you have compressed the original data. Okay, so after you have compressed the original data, and now you want to recover it back. Okay, that is, you want to recover it back from the compressed data. So lossless compression, it allows you to recover exactly the same compressed data that you had compressed with the help of the original data. So lossless compression is generally used for applications that cannot tolerate any difference between original and reconstructed data. That is, it is saying that if information is lost also, that some amount of when some amount of information is lost also, using lossless compression, it is negligible. Okay, it is not counted. Then we have types of lossless compressions also. That is, we have areas actually, as you can see. So one important area is text compression. Okay, so text compression, what happens is that it is very important that reconstruction is identical to the original text. Yes, that is, they're saying that when you are trying to use lossless compression in the area of text compression, it is very important that when you are trying to reconstruct the exact text. Okay, that is, you are trying to reconstruct the exact text to the original text, very small differences can result in statements with very different meanings. That is what happens when you try to perform lossless compression in text compression. You have to keep in mind that the reconstruction is identical to the original text, because what happens, small differences also can make large statements. That is, small differences can also carry out very different meanings. Okay, so suppose they are saying in bank records. Okay, in bank records, suppose you consider two statements: do not send money and do now send money. So see, this not and now, when you are using text compression, see, this is not, that is, this is T, and this is now, this is W. So see, a similar argument holds for computer files and for certain types of data such as bank records. So This is do not send money, do now send money. See, because of a simple error, that is because of this letter T has been this has been replaced by this letter W. See, the whole meaning has changed. Do not send money, it is saying, but this means do now send money. So this totally means the second statement totally means the opposite of the first statement. So this is a normal example of text. Okay, this is a normal example of text. So it is saying that text compression is very important for this is a very important area for lossless compression. So you have to use lossless compression in the area of text compression very carefully. So if data of any kind are to be processed or enhanced later to yield more information, it is important that the integrity be preserved. Yes, so what it is saying that if you want to process any kind of data, or suppose if you want to use that data later on, and why you want to use that data, suppose you want to use that enhanced or applied data, uh, suppose you want to extract more information from that, so it is important that integrity be preserved. So see, here integrity was not preserved, that is do not send money, it changed to do now send money, and the whole meaning changed. So you have to keep in count that the integrity of the data or message, whatever is being transferred in between the parties, are preserved. And integrity, you know, right? Integrity means you have to keep in mind that whatever information or data has been exchanged between the party is not altered or changed, or else the whole meaning changes. Then, say for example, suppose we compress the radiological image in a lossy fashion. Suppose now they are talking about some compressing some radiological image. Okay, so difference between reconstruction, say this is Y and this is original X. This was visually undetectable. So see, uh, when you just see this message, okay, this is Y, this is X. So for some moment you can't grasp the difference, right? You can't make out the difference. So this is visually undetectable. So if this image was later enhanced, the previously undetectable differences may cause the appearance of artifacts that could seriously mislead the radiologist. Since the radiologist is working on this image, suppose it has compressed, but Y becomes X. But the next time, suppose the radiologist, he wants to use this enhanced image for his work. So this previously undetectable differences may cause appearance of artifacts. That is, this is previously undetectable. That is why it turned to X. Yes, but it was not detected at that time. So this could seriously mislead the radiologist. Okay, so see, small differences may lead to larger meanings, and it may change the whole meaning. So because the price of this kind of mishap may be a human life, it may make, yes, because doctors, suppose sometimes what happens in prescriptions also, these things are not detected. So what happens, it may happen at the cost of some human life also. Okay, so it makes sense to be very careful to use a compression technique, to use a compression scheme or technique that generates a reconstruction that is different from the original. Yes, so you have to use, it is saying that lossless compression, you have to use these techniques very carefully. Okay, so this is about lossless compression. That is, lossless compression, the meaning is it involves no loss of information, but actually some part of the information is lost, but that is not detected by the human eye. Say for example these things, but you have to make sure that information, sometimes when information is lost, sometimes it is negligible. Yes, we make mistakes, right? The human beings, they make mistakes, but you have to make sure that that mistakes or that mistake, it doesn't say like it does it should not be such a serious blunder that it what to say now, means you have to make sure that whatever information is being lost, it is not, it is useless, that is redundant, that is not used at all. But you should make sure that important information is not lost in the process of when applying lossless compression techniques. Okay, so error-free compression or lossless techniques, there are some applications they require no error in compression. Say, as just now we told that, say in medical, in business documents, etc. Say medical, I give example of the radiologist. Then business, that is say bank transfer and all, the bank accounts. So some applications they require no error in compression. That is, whenever you use these type of compressions, you should make sure that there is no error. Okay, and there, when you use this lossless compression, you have to make sure that the compression ratio, that is CR, it ranges from 2 to 10 only. Okay, so from 2 to 10 only should be expected, not more than that. Then it make use of coding redundancy and interpixel redundancy. So error free compression or lossless compression, it makes use, or it takes the help of coding redundancy and interpixel redundancy. Okay, and I hope you remember these two terms. Okay, coding and interpixel redundancy. So here examples for error free compression is given as Huffman codes, then LZW, arithmetic coding, 1D and 2D run length encoding, lossless predictive coding, and bit plane coding. So we don't have to go through all these. We don't have to know everything. Say Huffman codes, then LZW, run length coding, and bit plane coding. These four types are very important. So we'll go through only these four types. Okay. So next we talk on run length encoding. Okay. So run length encoding, or in short you can also say as RLE. So this is a very simple form of data compression. Okay. So how this is used, this is stored as a single data value and count. Okay, this is stored as a single data value and count. That is, uh, say for example, let's first discuss this slide. So run length encoding, this is a very simple form of lossless data compression, as you can say, which runs on sequences having same value occurring many consecutive times, and it encodes the sequence to store only a single value and its count. Say, when I'm saying that it runs on sequences having same value occurring many consecutive times, that is, say for example, here you can see, consider a screen. It contains plain black text on a solid white background. Okay, so this is a white background and this is a plain text. So here you will get many long runs of white pixels in the black space and many short runs of black pixels within the text. So now see, this is an example of run length encoding. So what happens here, you can see here, we have two letters. Okay, we have this text consists of only two letters. This is a plain text, and this consists of two letters W and B, that is capital W and capital B. Okay, so what run length encoding it does, it runs on sequences having same value occurring many consecutive times. Yes, so it has this W and B, these are occurring, these are some sequence, and this is a sequence, and this is occurring many consecutive times. So what happens, run length encoding, it encodes the sequence to store only a single value and its count. Say for example, here count this W. So this W, we have 1 2 3 4 5 6 7 8 9 10 11 12. So we have 12 W's here. So this is B, this is only one B. Then again count 1 2 3 4 5 6 7 8 9 10 11 12. So this whole string, this is counted as, so when we want to write this, we the run length, with the help of run length encoding, so it encodes the sequence. So this is the sequence, it encodes the sequence to store only a single value. That is, suppose this is W, so we won't write this 12 W's as a whole, we'll only write a single value. So 12 W's means here we write 12 W and its count, so 12. So 12 is the count for this W. Yes, so with run length encoding data compression algorithm applied to the above hypothetical scan line, it can be rendered as this. So this whole text you can simply write it as this with the help of run length encoding. Okay, so this can be interpreted as sequence of 12 W's, 1B, 12 W's, then 3B, 24 W's, 1B, and 14 W's. Okay, so see, this is so interesting, and so this is very easy also when you want to when you want to perform this run length encoding on a very large text, you can say large string of text, you can use this thing. So the idea is to run a linear scan on the string, and for each distinct character we append the character and its consecutive occurrence in the output string. Okay, so this is same example I had attached it here. So say for example, so it is a very simple form of data compression. It is stored as a single data count, value, and count. For example, we have here 4 A's, double B's, triple C's, and double A's. So the solution we write as 3A, 2B, 3C, and 2A. Same thing, the same example I have taken it from the other slide. So the solution is this. Okay, then we go on to the second type, that is Huffman coding. So Huffman coding, this is also a very interesting type. Okay, this is a very interesting type of lossless compression. Okay, so this is actually the most popular technique for removing coding redundancy. Yes, so most popular technique for removing coding redundancies due to this Huffman. So Huffman, this is actually based on variable length coding. So remember what is variable length, what is fixed length coding? Yes, fixed length coding means the length of the code is fixed. If it is 3, the whole length is 3. Variable length coding means the code length, that is the code length, it keeps on changing. That is, we have variable lengths of code. Okay, then optimal code, that is, it minimizes the number of code symbols per source symbol. Okay, so we'll see this with an example in the next slide. Then Huffman coding yields the smallest number of code symbols per source symbol. Okay, that is, symbols are encoded one at a time. So we'll see this in the next. So first we'll just explain. So Huffman coding, also known as Huffman encoding. Okay, it is an algorithm for doing data compression, and it forms the basic idea behind file compression. Actually, Huffman coding, this is a very important algorithm for performing data compression, and basic idea is it is used in file compression. Okay, when you want to compress a file, then the most uh, popular technique is being used is Huffman coding. So here it talks about fixed length and variable length encoding, uniquely decodable codes, prefix rules, and construction of Huffman tree. So we already know that every character is stored in sequences of zeros and ones using 8 bits, right? So we are talking about binary bits, zeros and ones, and this is called fixed length encoding, as each character uses the same number of fixed bit storage, that is 8 bits. Okay, so suppose given a text, so how to reduce the amount of space required to store a character? Yes, so suppose you are given a text. So now how do you want to reduce the amount of space required to store this character? So the idea is to use variable length encoding. Okay, so we use variable length encoding. So here we can exploit the fact that some characters occur more frequently than the others in a text. Yes, that is, yes, definitely. Suppose you are given a text, you are given some texts, and it's not that all the text will be of same characters, right? It won't be comprised of the same characters, and frequency also won't be the same, right? So we can exploit the fact that some characters occur more frequently than the others in a text to design an algorithm, suppose, and which can represent the same piece of text using lesser number of bits. Okay, so what happens in variable length encoding? We assign variable number of bits to characters depending upon their frequency in the given text. Okay, so frequency of text will be given. That is, text will be given and frequency will be also mentioned for the number of characters. So you can calculate, you can assign variable number of bits to characters depending on their frequency. So some character might end up taking 1 bit, some might take up ending 2 bits, some will be encoded using 3 bits. Yes, definitely. Say some characters might take up 1 bit, some characters might take up 2 bits, some might take up 5, some might take up 6 bits, and so on. So problem with variable length encoding, it lies in its decoding. Okay, so encoding is not a big issue, but problem lies when you want to decode that text or the string. Yes, so suppose again, given suppose again given a sequence of bits. Okay, so given a sequence of bits, now how to decode it uniquely? So now you are given a sequence of bits, suppose. So how will you decode it? So suppose let us consider a string double A B A C D A B. So this is a string we have, and it has 8 characters: 1 2 3 4 5 6 7 and 8, and it uses 64-bit storage. So this string of character, it uses 64 bits storage. That is, it uses fixed length encoding. So this is fixed. So now if we note that the frequency of characters A, B, C and D, these are 4. That is, the character A has occurred in the string 4 times, B has occurred 2 times, C has occurred once, and D also has occurred once, respectively. Okay, so now let's try to represent this string of character using lesser number of bits by using the fact that A occurs more frequently than B and B occurs more frequently than C and D. Yes, definitely, because A occurs 4 times, B occurs 2 times, C and D occurs once. So we start by randomly assigning single bit code. Suppose we want to decode this, right? So now we start it with randomly assigning some single bits to, suppose let's say we assign a single bit, say 0 to A, then 2-bit code, say 11 to B, 3-bit code, say 100, that is 100 to C, and again 011 to D. Okay, so this we are using for decoding purpose. Now the string this will be encoded to, say, now put these codes in the string. So when you put these codes in the string, it will be encoded to 0, that is 00 110 1000 11011, and this is the division. Okay, that is, using the above codes you can encode it to this. Okay, but the real problems now, it lies in decoding, because suppose this is encoded. Okay, you tried to encode this string of characters with the help of these codes. Yes, but the real problem now lies in decoding. Why? You'll see. So if you try to decode this string now, it will lead to ambiguity, as it can be decoded to a number of, say, decoding. You'll get a number of decodings now. Say how? Say now, because this is just a string, this division we have shown it using this, right? But we only know that this is the encoding, this is the code. These are the codes which we have assigned it to this characters, right? So when you try to decode this, so you'll see you'll get a number of codes. So you can decode this at like this, you can decode it like this, you can decode it like this, and see, but you are not getting the, after decoding, you are not getting the original string of text. Yes, because why? You'll see, because see, A has 0 and D also has 0, right? A has 0, D has 0. So, and see, this is 011, suppose. Okay, so, okay guys, give me some time. Okay. Okay, so where was I? Huh. So suppose now you have encoded these, and see, after decoding you are getting so many types, right? So now what I was saying, that suppose A has been given, has been assigned a bit 0, and D has been assigned this 0 1 1. So when you look at this string now, don't consider this. You look at this string, you can't make out that is this is 0. Actually the string is double A B, but here this is A. Okay, this is A, this is also A, but see, when you consider these three strings together, that is this three digits together, you see 0 1 1, and 0 1 1 also has been assigned to D. So see, it has taken as ADA. So this has, the division has been given as this. So decoding becomes a very big problem when we consider these type of text. So now, to prevent ambiguities in decoding, we'll ensure that our encoding satisfied what's called the prefix rule, which will result into uniquely decodable codes. So now we will use a prefix rule here. So prefix rule is, it states that no code is a prefix of another code. Yes. So prefix rule means no code is a prefix of another code. So say A here is 0. So D can be, so D can start with 0. Okay, so A is 0, so so D also, so D can start with 0 now. So this is prefix rule. So we'll use this prefix rule, and now we'll see. So by code we mean that the bits used for a particular character. Yes, so these bits. So here in above example, 0 is the prefix of 0 1 1, right? So 0, this is the prefix of 0 1 1, which violates the prefix rule. So if our code satisfies the prefix rule, then the decoding will be unambiguous. So we have to change this code now. So let's see how. So consider the above example again. So this example we have taken again. So single bit 0 is being assigned to A, 1 0 assigned to B, 1 1 0 assigned to C, 1 1 1 assigned to D. So this time we assign code that satisfies the prefix rule to characters A, B, C, D. So now this 0 1 1 has been changed to 1 1 1. So using above codes, the strings this again will be encoded to this, that is 0 0 this. So put this codes in this string, and now we can uniquely decode this back to our original string as this. How? Because suppose you're given this string, suppose you're given this codes, right? So now encode it. So don't see this thing, don't see this division. So from here you can see 0 is 0, 0 is A, 0 is A, again 0 is A. Now what is B? B is given as 10, so 10. So what is A? A is 0, so 0. So then again we get C. C is 110. So this is 110. Then again, where were we? Then D is 111. Okay. Okay. So this is encoding. So we are looking at this encoding. So now we can uniquely decode this back to our original list. Okay. So how? Because now we are clear on variable length encoding and prefix rule. So now you got the idea what is variable length encoding, right? And what is prefix rule. So prefix rule is nothing but it states that no code is a prefix of another code. So simply you change this code to another code so that it does not violate the prefix rule. And when the prefix rule is not violated, it means the decoding will be unambiguous. That is, the decoding becomes easy. So now we are clear on variable length encoding and prefix rule. So let's talk about half-band coding now. Okay. So the technique works by creating a binary tree of nodes. So now we'll talk about binary trees. It consists of nodes. That is, a node can either be a leaf node or an internal node. So initially all the nodes are leaf nodes, right? Which contains the character itself, the weight, that is the frequency of the character, and internal nodes, it contain character weight and links to two child nodes. So as a common convention, bit 0 it represents following the left child, and bit 1 it represents following the right child. So we'll see this now again in an example. and the finished tree has n leaf nodes and n minus 1 internal nodes. I hope you remember what is a binary tree. Yes, students, do you remember what is a binary tree? Hmm? Hmm? Yes?
Yes, sir.
Okay. Okay. Then it will become easy for me to explain, okay? So it is recommended that Huffman tree should discard unused characters in the text to produce the most optimal code lengths. Okay, so the idea behind using Huffman tree is that it has to discard the unused characters, that is the characters which are unused in the text, to produce the most optimal code length. Optimal code means minimizing the whole code, okay, and only keeping the important ones. So let's see. So we will use priority queue for building Huffman tree, where the node with the lowest frequency is given the highest priority, and below are the given steps. So what happens in Huffman coding, that is we use when we are trying to build Huffman tree, we will use priority key, where the lowest frequency node is given the highest priority. And see, these are the steps. So first step is creating a leaf node for each character and then adding them to the priority queue. So you won't understand the steps. I'll just read it. Then with an example next slide you can understand. So first you have to create a leaf node for each character and then add them to the priority queue. So then while there is more than one node in the queue, so you have to remove two nodes of highest priority, that is with lowest frequency, from the queue. Then you have to create a new internal node with the two nodes as children, with the frequency equal to the sum of the two node frequencies. Then add the new node to the priority queue, and finally the remaining node is the root node and the tree is complete. So let's see what happens. So, so consider the text consisting of only A, B, C, D and E. Okay, so we have this text. So we have a text which consists of A, B, C, D and E and their frequencies. That is, frequency is nothing but the weight of these characters. Okay, so weight has been defined as 15, 7, 6, 6, 5. So 15 for A, 7 for B, 6 for C, 6 for D and 5 for E respectively. So this is the figure, and we'll illustrate the Huffman tree coding with the help of the algorithm, with the help of these diagram. Okay, so what it is saying, the first step: create a leaf node for each character and add them to the priority queue. But while there is more than one node in the queue, first remove the two nodes of highest priority. Okay, that is lowest frequency. So lowest frequency from the queue. So first remove two nodes of lowest frequency from the queue. That is, lowest frequency here we have of D and E. Yes, so we have to consider two nodes. Yes, because we are constructing a binary tree, so we definitely have to consider two nodes. So in this sequence of code, we check it and we see the frequency of D and E is the lowest. That is, first E has lowest, then D. So now construct. So now create a new internal node with these two nodes as the children and with frequency equal to sum of the two node frequencies. That is, D and E. Consider these two nodes, keep it in the priority queue and add it up. So 6 plus 5 is 11. So 11, this constitutes of D and E. So this queue consists of D and E. Now again, go to the next two nodes. That is, the next two nodes with lowest frequency is B and C. So consider B and C again separately. So B and C. So add up the frequency of these two nodes, that is 7 plus 6 is 13. So 13 comprises of B and C now. Okay, and then A. So next you see, add up these two again. We have to consider these two now. So add these up to, so 13 plus 11 gets to 24. So 24 consists of these nodes now again. And then finally A. So add up with again this priority queue. So 15 plus 24 gives 39. So finally this is the Huffman coding algorithm. Using the Huffman coding algorithm, we constitute this Huffman tree. But Huffman tree is incomplete because we haven't consider the bits. We have to consider the bits also. We have to determine the bits. That is, 0 is for the left node and 1 is for the right node. Okay, guys, give me another minute. 1 second. Oi. Sorry for the interruption, guys. Okay, so this is Halfman tree. Okay, so this is the construction of Halfman tree. So I think I went a bit fast today while explaining, right? So did you get the whole concept of Halfman coding and Halfman tree? Okay, so this is the complete structure of Halfman tree. That is, 0 is for the left, 0 is indicated for the left child node, and 1 means it is indicating the right child node. Okay, so see, the path from the root to any leaf node, it stores the optimal prefix code, also called the Halfman code, corresponding to the character associated with that leaf node. So this is Halfman tree. So how it has, so what is, so A is 0, what is B? See, B is 1 0 0. Okay, consider it from the root node. Yes, so path from the root to any leaf node, it stores the optimal prefix code. So the prefix code for B is, from the root is 1, then 0, then 0. Okay, then next is C. So 1 from the root, so from the root is 1, it is 0 and 1. So 1 0 1. For D, 1 1 and 0. Yes, and finally for E is 1 1 and 1. So this is the construction of Halfman tree. So guys, did you understand this whole concept? Yes? Should I explain again? I think I went a bit fast. Hmm? I'll share this.
Understood.
Hmm? Okay, you understood the tree, but you didn't understand the coding. So where did you get stuck? Okay. Okay, one sec, guys. I'm getting a call. Hello. Hi. Okay. So, okay, let's go back once. One sec. So, where did you get stuck, guys? So suppose this is a given. Say this is some text given. Okay, A, B, C, D, and E. Okay, you have particular weights, that is particular frequencies indicated for each text.
Ma'am, after coding, not the tree.
Not the tree. মানে কোনটো actually বুজি পোৱা নাই.
Ma'am, prefixত যে আপুনি decoding to বুজালে ডিকোডিং মানে মেম বহুত কেইটা কোড মানে মিলি যোৱা নাই
মই এতিয়াও বুজি পোৱা নাই কোনখিনিত
ওপৰত আৰু আপুনি ষ্টাৰ্টিং কৰিছে যে প্ৰিফিক্স চেঞ্জ কৰিছে যে
হা হা
0 to 1 1 to 0 সেইটো
আচ্ছা এক মিনিট হা এক মিনিট ৰবা BTM students don't join the class now, okay? I'm having DIP. First sem students, kindly don't join, kindly wait in the lobby, okay? Actually, I have another class now, guys. Do you have a free period today? Students, 7 sem কৰিছো তোমালোকৰ আজি কাইলৈ কৰিলে বুজিবা still I'll share this PPT with you guys. এবাৰ আকৌ চাবা just read this thing, okay? Just read this thing. মই actually বুজি নাপালো কোনখিনিত বুজি পোৱা নাই অলপ লৰা ধৰি হৈছে এতিয়া ফাৰ্ষ্ট চেমৰ ক্লাছ আছে actually. Okay? Okay, I'll explain tomorrow, or if you have a free period today, I can explain today also, or get back to the group after 1 o'clock. Then I can explain, okay? Like whenever you people are free, just poke me in the group.
Okay.
Okay. Okay, guys, I have another class, so thank you, okay?
Thank you, ma'am.
Okay.